Okay, we are going to talk about the section 3.3 differentiation rules. Let's see what we have in this chapter. Things are really getting easier in this chapter. We are going to be talking about the derivative of a constant function. At first, this is the simplest case. The formulas, the rules that we are going to go through here in this chapter 3, section 3, all actually they can be proven by using the limit definition of the derivative. Here, let's see, we first talk about the derivative of a constant function. Constant function is the simplest you can consider. Yeah, f of x is equal to c. The derivative of this is going to be 0. Okay? You can see actually the short proof here, which is y is equal to c is the blue color graph is the constant function, and if you see, we just form our limit definition of the derivative. We have x plus h, we have f of x plus h, we have f of x. If you take the difference, you're going to see that f of x plus h is f of x plus h is c, f of x is c, c minus c, you're going to get 0, and the limit of a 0 is 0. So the proof is very easy. Okay, we can also think about this as the values of constant functions never change, and that the slope of a horizontal line is 0 at every point. So we should keep this in mind. If you have a horizontal line, so the slope of the horizontal line is 0 at every point. That's why the derivative is 0. And let's consider x to the n. X to the n is an expression that we can use that to form our polynomials with, right? So x to the n is important. That's why we are stating it here. So what's the derivative of x to the n? X to the n is, as long as here the simplest case when n is a positive integer, you just take the power, put it in the front, and decrease the power by 1. So this is the derivative of a positive integer power. This is a power function x to the n we discussed long time ago, and this is how you're going to get the derivative of. Maybe I should make it a little bit bigger for you. Okay? Next, we have the general version of the power rule. If we have x and if we have the nth power of it, it's a, but in this case, n is any real number. It's not only integer like in the previous case. And if you want to take the derivative of this, it's the same type rule. Take the n, put it in the front, and decrease the power by 1. Okay? And there's a note here. This is going to be true for all x where the powers x to the n and x to the n minus 1 are defined. Okay? Derivative constant multiple rule. If you have a differentiable function u, this function u is a function of x, by the way, and let's say c is a constant that's given, arbitrary scalar, and c times the function, if you take the derivative of it, you can easily take the c out and take the derivative of u and multiply with c. Okay, the c in front of the function is not going to affect the derivative. You just take it out and keep it there though. Okay, don't erase that, keep it there, but multiply this with the derivative of the function u. Okay, and let's see. Okay, what do we have here? We have the y is equal to x squared, the blue color graph here. Let me see just a second. No, the yellow, the orange color graph is y is equal to x squared, and the blue color colored graph is y is equal to 3x squared. Both of them are parabolas, as you would know. And we want to know their slope at a point. But their slope at a point is the same as their derivative at a point, at that point. What's the derivative at 1? So here's, let's look at the y is equal to x squared first. Let me make it a little bit bigger for you. Okay. So we are going to compare these two graphs and their tangent lines and slopes of the tangent lines. Y is equal to x squared, for example. If you take the derivative of this, you are going to get 2x by applying the power rule. And if you apply this at 1, then you get the 2. So the slope at 1 for y is equal to x squared is just 2. Let's let's look at the red colored line, which is on y is equal to 3x squared graph. It's the tangent line to the curve at the point 1, 3. Okay? And we are interested in the slope. You take the derivative of this. We have this constant in front of x squared, which is 3. You take the derivative, you get 6x here, as you would see, right? And 6x is the slope at any point x. But they are asking us to find the slope at 1. So we have to evaluate this at 1. And 6 times 1 is 6. So the slope of this, as you will see, it is steeper. Slope of this tangent line is steeper, so slope is bigger, we expect. So slope is 6. On the other hand, y is equal to x squared is the slope 2 at the same point 1. So the line for 3x squared is the tangent line is steeper than the tangent line for y is equal to x squared. Which you can see this from the slopes as well. And slope is 3 times of the slope of the y is equal to x squared curve. Okay? So you're going to see this at every point. It's going to be just 3 times what you have at that particular point. If you look at it at 2, the point 2, definitely if you compare the slopes, one is going to be 3 times the other. Okay? Let's continue. How about if we have two functions and if we want to take the derivative of the sum of the two functions, what can you say? How would you write this in terms of the sum of the derivatives of the other two? Actually, we have a nice rule here. The derivative of the sum of the two functions is the sum of the derivatives. Okay? And let's see. Yeah, we have this curve here, x to the 4 minus 2x squared plus 2. Okay, and I want you to look at the points, special points, which are -1, 0, and 1. At those points, if you look at the tangent lines, they are horizontal tangent lines. Okay, which means their slopes are 0, which we have seen that when you have when you have such points like the curve is going down and going up afterwards, you have a peak down here. Okay, then you have a horizontal tangent line here, and the graph increases and then decreases. Later on, we are going to call them local max, local min. For example, this point is a local minimum point for the graph. So we are going, whenever we have local minimum values like this, local minimum means locally it's the minimum value it can take. If you just look around -1 and look at points that are close to -1, then and then if you look at the behavior of the function, -1, 1 is the value 1 here, the y value is the smallest value for this function locally here. You don't want to look at it globally, you just want to look at it locally. That's why it's called local minimum value. We are going to talk about this later on, I'm just telling you now. So when we have this type of local minimum value situation here, we have the horizontal tangent line because the derivative is 0. Here we have a local max. Locally at 0, at x is equal to 0, the value of the function is 2, and if you look at sideways to the right and to the left, the values are all less than 2. Okay, this is the local maximum value of this function, which is 2 at 0. Whenever we have such a situation, and we definitely have this, obviously we have this tangent line, a horizontal tangent line with the slope 0. Similarly, we have a local minimum value attained at the point 1 here, and the local minimum value is 1 here, okay, which is obtained at 1. Okay, and we have this horizontal tangent line here as well. But how are we going to show that the slopes are 0? We are going to take the derivative of this. derivative of x to the 4 minus 2x squared plus 2, if you apply the rules. Okay, let me do that for you here. I'm gonna go to my other page if I can. Okay, we just open up our notebook, OneNote, and we are gonna solve the question, which is okay, example that we were doing. Find horizontal tangent lines to the curve. I'm just changing the question a little bit, okay? To the curve y is equal to, let's get back to the question. Where is that? X to the 4 negative 2x squared plus 2. X to the 4 negative 2x squared plus 2. X to the 4 negative 2x squared plus 2. Okay, so that's the question. Just I made up a question here just to show you how we are going to find the horizontal tangent lines to it. And let's see, solution. What you're going to do, horizontal tangent lines are the lines which have the slopes there. The slopes are zero slopes, right? So what I'm going to do, I'm going to take the derivative of this. So we write this y prime for the derivative, and these are some of the functions. So I'm going to take the derivative of the first, and then this, and then this. Okay, we have a constant here. We have 2x squared, negative 2x squared here, and x to the 4. The derivative of x to the 4 is by using power rule for x cubed. And minus, we are going to apply this power rule plus a scalar multiplied function with 2. So I'm going to keep the 2. And the derivative of x squared, apply the power rule, 2 decrease the power by 1. And the derivative of a constant is 0. So let me rewrite that. Y prime is equal to 4x cubed minus 4x is equal to 0. Now, I equate this to 0 because I'm interested in at which points, we have the 0 slope, okay? At which points we have 0 slope? We have 0 slope. That's why I just equated to 0. And I wanted to find the x values. As you would see in the picture, we are going to find the x points where we have the horizontal tangent line. You're going to see it. Let me see just a sec. You're going to see that, okay? Let me go down a little, if I may. Okay, I would need a little bit more room here. I'm going to create more room here. Okay, I created more room. And I'm gonna go up, and here as you will see, I have this equation. So I'm gonna solve for x. We solve for x. Okay, so in here, which equation? Let me circle that. Okay, this is the equation that we are interested in. Okay, so I'm gonna factor out 4x because that's a common factor, and I have x squared minus 1, which is equal to 0. And from here, I have x is equal to 0, x is equal to 1, and x is equal to negative 1. As you would see, so these are the points that we have the horizontal tangent line. Let's get back to our picture. See, negative 1, 0, and 1. This is where the slopes are all zeros, okay? This is actually an example for in the book. Okay, we can even write in our, where is that? Let's see. Here, we can write that this is example 4, okay? Maybe I should write it here. Okay, this is example 4 in the book. Okay, so we found it. And if you okay, how about the tangent line equations? Okay, find the tangent line equations as well. So we found that at these points we have slopes. Okay, we have horizontal tangent lines. Okay, so we can say horizontal tangent lines are in here. Tangents at x is equal to 0, minus, plus 1. So what are the corresponding equations? Equations of the horizontal lines of horizontal tangents, I should say. You would need to find only the y value there, right? Okay, so what's our original original equation for the curve? X to the 4 minus 2x squared plus 2, right? This is the curve that we started with, that you see in the picture. So I'm going to just find the corresponding y value at 0, 1 and negative 1. So let me call this f of x. Okay, y is equal to f of negative 1. Okay, we just put it in, negative 1 to the 4 minus 2, negative 1 to the second power plus 2. So this is gonna give me 1 minus 2 plus 2, so this is 1. So this tells me the first horizontal tangent line is y is equal to 1. And the second one, at negative 1, of course, at x is equal to negative 1. The second one is y is equal to f of 0. Okay, just put it in. 0 to the 4 minus 2 times 0 plus 2. This is going to give us 2. Yeah, so this tells me that my second horizontal tangent line is, okay, y is equal to 2. Y is equal to 2 at x is equal to 0. So I have just found the equation form of, this is y is equal to 1, my horizontal tangent line. Y is equal to 2 is my second horizontal tangent line, and I'm gonna find my third one right now. Okay, just give me one sec here. Okay, I just created some more room down here. Alright, one sec. Okay, let's find the third tangent line, horizontal tangent line. Let's find it, and let me see. Okay, the third one is going to be, we of course by looking at the graph we can easily say what this is, but we want to write it down. We have to show our work, right? This is how we are showing our work. 1 to the 4 minus 2, 1 to the second power plus 2. So this is going to give you 1 minus 2 plus 2, so this is 1. Again, so we got y is equal to 1, but this is at the point x is equal to 1. So these are all different horizontal lines, even though it's they both seem to be, I'm sorry. So this is one tangent line, this is another horizontal tangent line, and this is the third horizontal tangent line. Okay, so that's how you would find it, and we can easily say we are done here. We found only the horizontal tangents in this question. Okay, next, let's see what's next page. Derivative product rule. So how would you, if you have two functions, if you want to take the derivative of the two, derivative of the product of the two functions, then how would you do that? Can you take the derivative in terms of the derivatives of each? Yes, you can. And here u and v are differentiable functions at x, and their product uv is also differentiable at x, and the derivative of the u times v is going to be keep the first function as it is times the derivative of the second plus take the derivative of the first times the second. Okay, that's the derivative product rule. And then we have the derivative quotient rule. We are going to solve some problems on that. If u and v are differentiable functions at x, and we assume that v of x is not 0, then the quotient u over v is differentiable at x. How would you get the result? The derivative of the quotient is equal to, you take the derivative of the numerator, times it with the denominator, minus, you keep the numerator as it is, times it with the derivative of the denominator, and then all over square of the denominator. That's the rule we have. Okay, let's solve some problems here. I'm going to make up some problems for the product rule and the quotient rule, as you would see. Okay, let's open up a new page. We are going to open up a new page, but I have to make some copy paste here. Okay, alright, so this is gonna be page 2. Alright, so I'm going to give you a couple examples. I'm gonna make up these. They are not from the book, but you can easily, okay, make up your own examples. Example 1. Okay, find the following derivatives. Let's say find the following derivatives. Okay, so here I'm gonna make up the question. The first one is f of x is equal to x squared plus 5x plus 1, and then I'm going to write another function here, x cubed plus 9. Okay, so we want to find the derivative of this. B, g of x, let's say g of x is the ratio of the two, x squared plus 5x plus 1 all over x cubed plus 9. Okay, I created these two examples, and I'm gonna do the solutions right now here. Okay, let me get back to the red color. Okay, solution for A. Okay, so let's do that. Okay, the derivative of f with respect to x is gonna be, so I'm going to keep the first function as it is and take the derivative of the second, x squared plus 5x plus 1. Take the derivative of the second, that's what it says. Okay, plus, okay, take the derivative of the first, and times it with the second one. Keep the second one as it is. Okay, I have to move a little bit to the right. Alright, okay, just a little bit more. I'm trying to close my parentheses here. Okay, because of this I think I can. Let me move this away. Okay, I'm gonna move this thing down here. Alright, good job. Okay. Let's close this parentheses. Okay, we move down here. Okay, so that's we are not done yet. We are gonna finish it after we do this. df dx is equal to x squared plus 5x plus 1. 5x, I'm sorry, let's erase this. Plus 1 times the derivative of the, so this is the power rule, the derivative is 3x squared, take the 3 in the front, this decrease the power by 1, plus the derivative of a constant is 0, and my answer is just this. Okay, plus take the derivative of this. This is power rule, derivative of a constant. So it's going to be 2x, take the 2 in the front, decrease the power by 1, plus derivative of x is 1, plus the derivative of 1 is 0, times x cubed plus 9. Okay, we want to rewrite this to see it better, and the derivative is going to be, it's equal to, I'm not going to expand it, so 3x squared, x squared plus 5x plus 1 plus 2x plus 5 x cubed plus 9. So if you leave it like this, that's fine, no problem. Okay, that's acceptable. You don't have to expand it unless the problem wants you to do. Okay, so that's the final answer. Done. Okay, let's do B. Okay, in B, on the other hand, we take the derivative of the quotient. Alright, so the derivative of the quotient, df, this is g, by the way, I'm sorry. G is the ratio, the quotient, dg dx, or g prime at x, either way, g prime at x, this is also okay. Okay, we have to apply the quotient rule. This is the quotient of the two, this is the quotient of two polynomials, so I'm going to copy that down. Okay, so this is the same as, I'm sorry, the derivative with respect to x is x squared plus 5x plus 1 over x cubed plus 9. Okay, so we take the derivative of the numerator. Okay, so this, probably I should leave a little bit more space here. Okay, so dg dx is equal to, okay, the derivative of x squared plus 5x plus 1 times it with the denominator minus, keep the numerator as it is, okay, multiply this with the derivative of the denominator. The derivative of the denominator. Okay, all over this thing, and we are gonna just square the denominator. Just square the denominator. Okay, are we done? Not yet. We have to evaluate it. We have to apply it. This says you should take the derivative of x squared plus 5x plus 1. We have not done this yet. So let's continue. And okay, here, this big thing here, x cubed plus 9 to the second power. Maybe I should erase this. Okay, otherwise you may misunderstand. This is the denominator of our expression. Nothing we are going to do in the denominator, but in the numerator we have to evaluate the derivatives, right? So the numerator is 2x plus 5 times x cubed plus 9. Okay, so this is the derivative of x squared. Take the 2 in the front and decrease the power by 1, plus the derivative of x is 1, so we have 5 left. The derivative of a constant 1 is 0, so we don't write that here. Minus x squared plus 5x plus 1, okay, times 3x squared. Okay, 3x squared. Alright, so that's the expression. You can either simplify it. Let's simplify it. Usually we don't ask you to simplify it, but I want to just simplify it here. So you just distribute this over 2x to the 4. If you have to, that's how you would do it. That's why I'm doing this now. Okay, plus 5x cubed plus 45, and then minus 3x to the 4 minus 15x cubed minus 3x squared. Okay, all over x cubed plus 9 to the second power. Now I'm gonna use the red color here. So I may do some cancellations. So I have this cancels with this. Okay, I'm gonna use green color for another simplifications here. I have 5x cubed, I have negative 15. Okay, and that's it. I think I don't have any other, so I'm going to rewrite the final version, final expression. But as I told you, you don't have to do it unless I ask you to do it. Okay, usually I'm not going to ask, but I'm just doing it in case you would have to do it. Minus x to the 4, and then minus 10x cubed. Okay, minus 3x squared plus 18x plus 45 over this expression. Okay, that's the final answer. Okay, so you can either write it like this, okay, done, or you can write it like this in compact form. Either way is fine. So this is also fine. Okay, let me circle it. This is also a good answer. Okay, all right, so that's how you would do the quotient derivative, product derivative. Okay, derivative quotient rule and derivative product rule. Okay.